So the talk will start in a very non-technical, almost confusingly so way, and then suddenly become technical and confuse you even more. Right, so our mandate is, as a research institute, we operate within the Royal Bank of Canada, so RBC, and we're based in a number of cities in Canada, so we're fully Canadian at this point. And our mandate is to perform both fundamental and applied research in AI and machine learning. So we are a research institute within a bank, and I know it sounds weird, but it really is established and designed to create the right environment for researchers to continue working as they are used to when they graduate from the various PhD programs in machine learning. The applied group within the lab is actually building products. So we build AI-based products, mostly in the financial services space, but the products themselves are not always related to fintech. And so we'll talk about one of the areas of research that we're working on, which has to do with privacy. So this is who we are, and this is the least technical slide in the presentation. We're a bunch of, it's a kind of a mixed collection of people from a variety of backgrounds, a variety of fields, entrepreneurs, academics. The people who have the labels attached to them in the picture are neither entrepreneurs or academics, but the rest of them are, interestingly enough. We've been building this in the past 3 years or so, both trying to retain some of that talent in Canada, and no offense to this amazing city, but it took a lot of the talent that came out of Canadian universities, and so we're trying to create an environment for them to stay back. And we're currently working coast to coast, so West Coast would be Vancouver, and East Coast is Toronto and Montreal. All right, so the topic of the presentation is around privacy. And for the most part, I'll talk about generally the area of privacy-preserving AI and some of the techniques in that space. And I'll mention briefly some of the work that we're doing as well. So first of all, why care about privacy at all? I mean, as a company, privacy is something that typically comes as a requirement. It's influenced by compliance and legal and contractual obligations. It's almost never the goal, at least for most companies, right? And so at Borealis, we're thinking of privacy actually as a competitive differentiator. As you build more and more complex AI models, and as you create models that provide real benefit based on data that is rich and meaningful, so things like information you have from text, from images, things you don't necessarily want to disclose publicly because it would affect the privacy of your customers. But you want to benefit from that data, and you want to provide services back to these customers that will make them happy. And so privacy, especially in the context of a bank, which is a highly regulated organization, is a very crucial component of AI. In fact, it's almost impossible to do anything that is exposed to the customer or that has any kind of external visibility that does not properly address privacy concerns. And that's, in my opinion, a really good thing. On top of this, security is something that's constantly in the news. So we keep hearing about it. We've been hearing about it all the way back to all the kind of breaches that happened, Snowden, all the hacking that's going on. So everyone knows that their data is out there. Everyone is wondering what's happening with it. And leading with privacy actually addresses one of the core fears that customers have when you tell them that you're doing something interesting with their data. One thing that's worth mentioning is the European Privacy and Compliance Framework, the Gdpr. So for those of you who haven't heard about it, and I'm not a compliance guy, so I would never talk about anything like that except for GDPR. This is a very strict framework that affects almost every company that has data in the world, because it applies to any company that touches European citizens. And it has strict requirements on what needs to be done in terms of disclosure, opt-in, and notification of anything that leaks about the customer's data. And one of our objectives was to, going back to, in complete contradiction to what I started with, going back to compliance, address one of these very strict requirements that come from the European Union. So what is the problem statement? Generally, within businesses, data is siloed. So if data sits within a particular organization or a particular company, it cannot be easily accessed by other companies. Right? It's because of compliance, it's because of data rights, but it's also because of reputational risk. So typically, if you're a startup, or if you're a bank, it doesn't matter. If you're building predictive models, these models will exist per customer if you're still selling to other businesses, or per business unit within your organization. Right? So you will never be able to take data from, let's say, 10 different companies, pull it together, and create the best possible predictive models for your customers. This is just something that doesn't happen. On top of that, if you're selling AI products, you're usually in direct competition with data science teams within your customer base, right? So imagine again, you're a startup, and most of my examples come from that world because that's what I've been doing most of my life up until I joined a bank. So when you're selling, to another business, typically there's a data science team within that business that wants to know whether you're replacing them or whether you're competing with them. And it's never a good situation to be in. So the objective that we always had in mind is how do we create value that is not competing on algorithms, which of course is important. Building algorithms is the main goal of any AI lab. But how do we create data network effects that overcome these privacy limitations and these silos? And finally, many of the folks on the team, myself included, deeply care about privacy overall. So we think that it's something that goes down the list of priorities way too quickly, and we personally believe that for society, it's a very important area to emphasize. All right, so fine. So, okay, let's say you agree that privacy is important, but I'm removing all the PII. PII stands for personally identifiable information. So I remove people's names and social security numbers and addresses. So I'm good, right? Like I've anonymized the data. Well, not quite. So there are examples, some very prominent and others kind of more researchy, of data being fully de-anonymized even after being stripped of what's called personally identifiable information. And the main reason for that, and I'll go through these examples, but the main reason for that is that while a particular data set may be anonymized to a large extent, there's a lot of public data available that you can cross-reference with. Right? So consider a simple example where you have a table of salaries, and the table includes a person's name along with their role and the salary that they get paid, and let's say the gender, and you strip it of the name, right? Name and age or whatever is considered identifiable. And so now it's anonymized technically, but then if you take the role and let's say the gender, you've reduced the list of people that could be the people that this role belongs to significantly, and especially for more senior roles, so when there's kind of one of that type of person or maybe a few, you've really effectively identified the salary of that individual. So some practical examples of these types of de-anonymization attacks are, the most famous one is the Netflix competition. So Netflix used to run, I don't know if they still do that, a recommender system competition for academics. They would publish an anonymized data set of viewing records for movies, and they would ask competing labs around the world to produce recommender systems. And so while the AI researchers were working on recommender systems, the privacy researchers were working on de-anonymizing the data set. And so sure enough, they were able to identify the viewing records of a particular individual, which then filed a lawsuit that was settled out of court. A more public and kind of, dramatic example would be the medical records of the Massachusetts governor. So that was a case where the Massachusetts health system released an anonymized data set of medical records for research, and that was, very publicly, as far as I remember, if I remember correctly, it was very publicly advertised by the governor. And so privacy researchers then went in, cross-referenced that data set with public data and found the governor's medical records in there. And so this gets creepier and creepier as it goes down the list. So there's an example of a DNA being identified, and of course, that could have all sorts of implications, especially if the person has, certain genetic health conditions. And finally, this, line, I think in Mandarin, stands for Human Flesh Search Engine. And basically, this is a crowdsourced way of digging up dirt on people. So you can actually spin up a crowdsourced campaign and find information about individuals on the internet through various forums and kind of sources. So the bottom line is, while a particular table or a data set may feel anonymized, there's plenty of information out there that can provide stronger priors on which person the particular record belongs to. And that probably, then that's my hypothesis, underlies the reasons for the lack of trust in existing anonymization methods. Right? So if these methods were really trustworthy, you could probably just use them and share data across organizations, but that doesn't work. You can't do that today. Right, I'm going to speed up because I'm talking a lot, and there's still a lot to go through. So toward real privacy, okay, fine. So dropping PII doesn't work, right? But if you think about it, it's really a structured way of destroying information. So if you think about a particular record in a table as bits, you're really just setting a subset of these bits to 0, right? And sure enough, if you set the entire record to 0, so if you took your data set, the binary representation of that data set, and just set all the bits to 0, that would be truly anonymous because it contains no information. So then the question is there something in between that's a bit more rigorous, where you destroy information in a structured way that both has provable guarantees, but also kind of preserves the value in the data, right? And it's important I mentioned provable. That part is particularly important because the existing methods that don't work also don't have the backing of the experts in the field. So the privacy community says that they don't work. Right, sorry. So before I go on, so the method that I want to introduce, and most of you have probably heard about it, is called differential privacy. And so this is a framework or a set of definitions that describes what it means for a machine learning algorithm, or more generally an algorithm, to be privacy preserving. It was defined originally by a group of researchers at Microsoft Research. So I think originally it was a team working with Cynthia at work, but it became kind of a field of its own, which intersects both privacy and AI. And what differential privacy stands for, and we'll talk about the formal definition, is really a way to guarantee a very strong notion of privacy for a particular data set or a particular algorithm, right? And that is something that comes with mathematical proofs and the support of the privacy community. And so for a very long time, differential privacy was a purely academic exercise, generally seen as not very applicable in practice, until Apple, back I think in 2017, in their April event where they announced new products, they've also announced that they're going to be protecting customers' data and customers' AI models with differential privacy. And Apple is generally very good at announcing and kind of publicizing these types of things. And so, of course, suddenly it became this big thing, and it was written about in the Wired magazine and, in various other publications. And it was no longer this academic curiosity. It was actually a real thing that a major company is doing. And so, right after that, Google, turns out, Google was also using differential privacy in production in their Chrome browser. But they haven't advertised it as much, and so they were like, hey, wait a minute, we were doing this first, but too late. Okay, so that was, it was really fun to watch this unfold, and especially for people who actually care about, this space of privacy research. And so today, there's a number of companies that use differential privacy. So one logo that's missing from here is Uber. Uber is actually developing and open sourcing tools that allow differential privacy to happen. I won't go into too many examples, but we are also working on research and products in the differential privacy space. Maybe one example that I'll mention is actually the Google one, because it's really, really kind of both simple and interesting. So in the Chrome browser, generally, and this is my understanding, so I could be wrong about the exact reasons that they do this, but then Google doesn't track the browsing history of the users of Chrome. However, they do want to identify when new malicious domains pop up on the internet. So these are domains that didn't exist up until a day or two ago and suddenly get a lot of traffic. How could you do that before there's any public linking to these domains? Nothing links to them, and yet compromised machines access them, right? So if you could track people's browsing history, you could just see which domains suddenly have a spike in popularity, but you can't. So what they've done is they've built a differentially private aggregation approach into Chrome that tracks, general spikes in popularity in access to new domains, but in a way that does not allow Google to know which browsers access these domains. So it's a really cool solution to this problem, I think. All right, so let's stop for a second. So we've been talking about what differential privacy is and who's doing this and why. This is a general observation. Once you bring up privacy or security, it's a psychological thing where nobody says, no, it doesn't matter, right? So imagine a room of execs, especially at the bank, discussing, use of data, and somebody says suddenly, hey, we got to consider the privacy implications of that. Can you imagine someone else in the room saying, no, forget about privacy, let's just make some money, right? So that doesn't happen, and this is just a general suggestion for those who care about privacy and security. Once you bring it up and you have a concrete point to make, it generally sticks. And so that's what we've seen with privacy as well. As long as no one knows how to solve it, it kind of goes under the radar, or it becomes a compliance or contractual thing. But once you have a solution, suddenly everybody wants to be the ones that protect customers' privacy. Right? So what is differential privacy? Let's get a little bit more technical. So generally, it's an approach to gain insights or create models on data sets, but preserve the privacy of individual records through structured noise. And so what you see in this diagram is a typical example of what a machine learning pipeline might look like. So imagine each of these customers on the left is either an individual or a business. And you've collected a bunch of data points from them. So it's either information that's collected on a phone about your activity using that phone, or if you're a business, it's your own data set that understands customer behavior, let's say. And so you're creating an AI model, machine learning model on top of it. And then what you would like to do is to aggregate all of these models and create one mega model that understands everything in the world, right? And so what can you do to make this private? As long as you make it private at any point in this chain, you're good to go. And this is kind of a property of differential privacy, that it propagates. Once you've made something private, you cannot unprivate it, right? And that's the whole point. So there are methods in differential privacy to introduce noise at basically every step of the way. So either to the raw data, or to the process of training a machine learning model, or to the process of training an aggregate model, or finally to the actual query response that goes out of that model once you pass some data through it for inference. And there are mechanisms for each of these. So what does differential privacy not guarantee? And this is before we talk about what it does guarantee. So it doesn't guarantee that a particular individual's data has no impact on the model or on the outcome. That would mean that you're not using the data. It does not guarantee that no one can learn anything new about an individual, because even if your data is not in the data set, maybe the data set talks about a particular demographic group that you belong to, or a particular geographical area where you live. And so it's possible that even if the model is fully private, it contains information that is relevant to you as an individual. It does not guarantee that you cannot be rubber hosed, so that's a type of attack in the security community. That's when you're kidnapped and being forced to disclose information. And of course, all the other things, that academics can be trusted and that code does not contain bugs. So none of this is guaranteed by differential privacy. What it does guarantee, though, is in an intuitive sense the following. If there were two universes where in one everything is identical, but in one of the universes Alice's record is not in the data set, while in the other universe it's in the data set, and everything else is the same, including all the randomness in the universe, then nothing really will change, basically. That's the intuitive guarantee. So these two universes will continue to perform exactly the same, or the same things will continue to happen in these two universes, right? And so one of the implications of this guarantee is that a model that is differentially private cannot be reverse engineered back to the original data. Because imagine if it could, then you could also reverse engineer the model that does not contain Alice's data, right? So you could recover Alice's data from a data set that doesn't contain it. And so that's kind of the point of the guarantee, that you cannot do that. So one more thing I want to say, and my slide with the equations disappeared somewhere. Okay, no, it's still there. All right, so I just want to skip to the formal definition. So let's talk a bit about how it actually looks in practice. So think of an algorithm that you want to show to be private. And think of all the possible outputs of that algorithm. The constraint that differential privacy imposes is that if you change only one record in the input, so imagine X and Y are data sets that differ by a single record, then the probability that the algorithm will output something different between these two data sets is at most multiplicatively exponential in a privacy parameter called Epsilon. So this is the part where it becomes very technical and everyone gets confused, right? So let's make it more specific. Think about an event that is extremely unlikely. So it's 1 over a billion or 1 over a trillion in terms of probability. And you're really worried about this event because it would be a really bad event, right? So an example would be somebody recovering Alice's raw data from interaction with your website. So the likelihood of that event when Alice's information is not in the data set is very low because there's, if anyone can recover that data, they could have just guessed it without looking at your model or your data set because the data is just not there. Alice's data is not there. The probability of that event, which was close to 0 without Alice's data, remains close to 0 if you introduce Alice's data into the data set. How close to 0? It depends on this privacy parameter Epsilon, which is a very important parameter. So this parameter is a trade-off it influences a trade-off between the accuracy of the model and the level of privacy that you get. Right? So if epsilon is 1,000,000, then your guarantee here is that your probability of a bad event is not more than e to the 1,000,000 bigger than it used to be, which is not a meaningful guarantee. But if epsilon is, let's say, 2, then the probability of your event is not more than, let's say, 8 or 9 times bigger than it used to be. So if it was close to 0 before, it remains close to 0 after you've added the record. I'm out of time, but I'll maybe skip quickly to some applications that we have in mind. So first of all, something that is not directly related to banking, but accessing medical records for research purposes would be the use case that I think is most interesting in this case. Right? So this is a very significant constraint on AI researchers, that they cannot access medical records if they want to develop applications of, let's say, deep learning or traditional machine learning methods in healthcare. And so accessing this data through differential privacy could alleviate those constraints. Meeting compliance requirements, of course, and restrictions on information sharing within organizations, right? So if you could build a model that's privacy preserving, that convincingly guarantees to the customer that their data is not at risk of leaking, and that whether their data is in the data set or not would not affect them personally, despite the fact that your company uses their data, those are powerful guarantees. And of course, applications like fraud and KYC, so know your customer, across multiple banks. And so we are working on that with the Vector Institute in Toronto and with the other Canadian banks. Right? So this is all. Thank you.